lecture introduces testing methods that can be used to test implementations of abstract data types. Testing is one of the most crucial activities in software development. Any code we write or modify needs to be tested before it can be used in production or live systems. There are two important goals to testing. First, testing ensures that our class behaves as written in the specifications. This is called verification. The classes that we write are used along with many other classes to create a program, and each individual class has specific actions that it must perform so that the overall program runs correctly. If the class does not meet its requirements, other classes that use this class as a data member or client may fail to perform successfully also. So when an item is added to our collection, in this case our bag interface implementation, we need to verify that the item was added. When a specific item is removed, we need to verify that the requested item is removed. The second important goal of testing is validating that our class has no errors. Our implementation must work as expected and not lose or modify data outside of its responsibility. The data structure that implements an ADT should be consistent. When items are added to the data structure, they should be added and not lost or break the data structure or how we track items inside the data structure. Testing methods, classes, and programs should always follow some type of plan. Never do haphazard testing. Without a plan that tests and validates an ADT implementation part by part, it is extremely difficult to pinpoint exactly where an error occurs, and so we may break code that was functioning correctly or duplicate tests expecting different results without changing the code that caused the actual problem. A good test plan focuses the testing so it is clear where errors occur or improper behavior breaks methods. There are two methodologies we can use to develop a good test plan. The first is unit testing. In unit testing, we focus our testing on the implementation of specific classes. We want to ensure the class performs as required. By focusing on one class and its specifications, we know that any errors that arise are in this class. Once the class is thoroughly tested, it can be used with confidence in programs and other classes. An important tool in unit testing is the test harness or driver class. This is a class or program that is designed to test a specific data structure and calls all of the data structure's methods and tests them to ensure that the data structure performs correctly even in extreme situations, such as when our bag would be full and we try to add an item, or when the bag is empty and we try to remove an item. For unit testing, we implement our code in pieces and test each piece before implementing additional functionality. For example, we decide to test the data fields for the class and then implement methods that provide core functionality, such as constructors and methods to add and display items. Then we test those methods before continuing. Next, we implement one or a few methods that are more involved and test those. Once those pass our tests, we continue implementing and testing additional methods until the class is complete. It is crucial that this iterative approach is used even now. Implementing ADTs require classes that are more involved than you may be accustomed to. The programs are going to be more complicated and require more classes also. Implementing and testing code in small parts saves hours of debugging time. System testing follows unit testing. System testing tests how classes work together. This can be done with several related classes, such as those that form a package, or it can be all of the classes that form a program being tested together. System testing often relies on the use cases that were developed during the design phase of building a program. The classes that comprise the program are tested in workflows that would occur during the use of the program. Unit and system testing methodologies guide us in designing our tests, but what exactly do we test? This is where the idea of black box testing can guide us. Black box testing treats the class or data structure being tested as a black box that we cannot see inside. How the black box is implemented is not important, only that the box functions the way it is specified. When the box is fed a certain input, it should respond with a specified output. In black box testing, we are only concerned with functionality of the box or class and the interfaces to it. This means that we can test our data structure based on the interface that it implements, since how that interface is implemented is not important. The implementation is not important to the testing, but the implementation is important when it comes to fixing any errors or bugs and resolving any inconsistencies the testing discovers. And black box testing can be used for both unit and system testing. Now let's look at some of the specifics of developing tests. First, for unit testing, we want to validate the status of our collection after we've added or removed items to our data structure. We want to ensure the bag is full or empty when it should be full or empty. And we want to display all of the items in the bag to validate that each item that should be in the bag is actually in the bag. We also need to validate the status of individual items as we add and remove them. This is a different problem than validating the status of the collection. For example, we may check each item after adding it to the bag and validating that it was successfully added, but the bag may return that it is still empty. In testing any of our ADT implementations, we want to make this distinction between testing the success of adding or removing individual items and validating the status of the entire collection. With this in mind, we can begin to develop a unit test plan for our ADT bag implementation. Let's focus on the methods themselves and see how we can test the functionality of this class. To start, we need to create an instance of a bag to test. A newly created bag should be empty, so we need to check that. Next, we can add items to the bag and validate that the bag has all of the items added. And also check that each specific item is in the bag. If the items we added were added successfully, we can remove random items and then specific items from the bag. Then we can continue adding and removing items, but we want to validate two important boundary conditions: that the bag is full when it should be full, and that the bag is empty when all of the items have been removed. This is a different condition than when the bag is first created and is empty. Now that items have been added to and removed from the bag, if our internal accounting system for the bag has an error, the bag may not realize that it is empty. Three important methods we need to be aware of are the add and to remove methods. These methods change the state of the bag. In our test plans, we want to ensure the status of our data structure is validated anytime methods that change the data structure's state are used. Here's a skeleton for a driver program that can test an instance of our bag class that holds string objects. The code for the specific test goes in the main method, and there are several helper methods shown here in orange that can be called to perform tasks we need to repeat several times. A very important aspect of this driver class is that we use the bag interface instead of the specific bag implementation as a parameter to the helper methods. This generalizes our driver so that it can be used with any bag interface implementation that holds string objects. We have a set of helper methods that shows us the status of the bag. Show bag stats calls get current size and reports those to the user. The display bag method calls the bag's toArray method and then displays the items in the bag for the user to validate. The add to bag and remove from bag helper methods add and remove items respectively, but also validate that the correct item was added or removed. Looking in detail at the main method, we step through a series of tests that use the helper methods to manipulate and validate the bag. Here we instantiate our bag. Since we are performing black box testing, we are only interested in the interface's functionality, so our test bag is of type bag interface. We cannot instantiate an interface, so we instantiate an object from a class that implements the interface, the class we want to test. After creating the bag, we check to make sure it's empty and display its status. We then add values to the bag and display the items to ensure they were added correctly. Then the bag is empty or cleared, and we add items and check each one after we add it. Following that, the status of the entire bag collection is checked again. With several items still in the bag, the remove methods are tested. Either a random item is removed or a specific item is removed. If a specific item is removed, it must be checked to validate the correct item was removed. When our bag implementation test driver is run, we see testing output that shows the activities our bag was put through, the bag's status at various points in the test, and validation of the adds and the removes. Once we are satisfied that our bag implementation has passed all the tests and we believe it is functioning correctly, we can do a system test. We combine our bag implementation with several other classes to create a program that performs some real-world function that requires our class. In this example, we create a piggy bank that stores coins. The piggy bank holds all of the coins but does not organize them, and there may be duplicates. So our bag class is a good abstract data type to use as a data member. The piggy bank class can then be a simple wrapper that lets the client add coins to the piggy bank by adding coins to the bag, removing random coins from the piggy bank by removing a random item from the bag, and then checking to see if the piggy bank is empty by checking to see if our bag is empty. The data member is of the type bag interface. This gives us flexibility in what implementation we use to hold the coins in our bank. In the constructor, we instantiate a bag implementation. If later we find that a better implementation of the bag interface exists, we only need to change this one statement in our class to use that new implementation. Here is a program that uses our piggy bank class to add and remove some coins. We declare our piggy bank object here. And even though we appear to be testing our piggy bank program and piggy bank classes, we are testing also how well our bag implementation performs. On larger programs that store hundreds, thousands, or millions of items, we may want to test several different implementations of our interfaces to see which performs the best with the usage described in the specific example.